Today, it's my pleasure to talk about some of the results that came back from NASA's gravity mapping mission that's called GRAIL. And even if you've never heard of this mission before, you should recognize the acronym because this mission is almost exactly the same as the GRACE mission, which is currently flying around the Earth, making gravity measurements of the Earth's gravity field. And the GRAIL mission is pretty much exactly the same mission. They just sent the same two spacecraft to the moon. And the only difference between GRACE and GRAIL is that GRACE is more concerned about measuring time variable gravity signals for the Earth. And for GRAIL, we were only concerned with measuring the static gravitational field that doesn't change with time. So first, the question is, why do we need to send these more missions to the moon? And why do we need to measure the gravity field of the moon? This is a common question. And it's because for the moon, we actually have a lot of data. We have global spectral imaging, which gives us information about the mineralogy. We have images of the surface, which gives us information about geomorphology. We have information about the composition of the surface. And we also have almost 400 kilograms of samples that were collected during the Apollo and Lunar missions. Now, the problem is that almost all of these data sets are mostly concerned about the surface. And if you want to see below the surface, kilometers or tens of kilometers or even 1,000 kilometers below the surface, you really need to have some geophysical data. And one of the key geophysical data sets that we have is related to the gravitational field of the moon. And this is because gravity is proportional to mass anomalies. So this gives us information about how mass is distributed below the surface. Okay, so this talk is going to be very short, but this is just a brief outline of what I'll go through. First, I want to give a brief overview of the GRAIL mission itself. I will go through some of the initial results that were obtained from the initial mapping of the moon's gravity field. Then I'll go into some more scientific questions concerning impact basins and also a question about whether the mantle of the moon might be exposed on the surface. Okay, so how do we measure gravity? Well, we have measured the gravity field of almost all of the terrestrial planets and outer planets in our solar system. And the way we generally do this is we send a spacecraft, put it in orbit, and we send a radio signal back to the Earth. And what we do is we measure the Doppler shift, and the Doppler shift gives us information about how the satellite is being accelerated. Now, this works great for Venus, for Mercury, for Mars, and for the Earth. But for the moon, there's a problem. And that is that whenever the spacecraft goes behind the moon, we cannot communicate directly with the spacecraft because the moon is in the way. And because of this, for the moon, we have very little to no direct tracking data over the far side of the moon. And because of this, the near side gravity field of the moon was known fairly well before GRAIL, but the far side was very, very poorly known. So this is why NASA decided in 2007 to select a Discovery class mission called GRAIL for Gravity Recovery and Interior Laboratory in order to improve upon our knowledge of the moon's gravity field. Now, if you're not familiar with NASA Discovery class missions, these are very rapid missions. It was selected in 2007. They gave the PI, who was Maria Zuber, about $450 million US. She built and launched the spacecraft about 3 or 4 years later in September of 2011. And then it took about roughly 3 months for the two spacecraft to cruise to the moon using this kind of weird trajectory that I'm showing here over on the left-hand side. The spacecraft were inserted into orbit at the end of the year. We spent 3 months circularizing the orbits, and then we had a 3-month primary science mission where we mapped the gravity field from 50 kilometers altitude. And then after that, we waited a couple months and we had an extended mission for roughly 3 months where we mapped the gravity field at a lower altitude of 20 kilometers. So this is a very, very quick mission. Between the launch and the end of the mission, it was just over 1 year. And this is, let me just turn the volume down, sorry. This is just a video just showing the schematic of the mission. Here are the two spacecraft being circularized into orbit. Once they're in their science phase, they link up and they start sending a microwave radio signal back and forth between the two. And what we do is we measure the distance between the spacecraft with a precision on the order of a micron. And we mapped the the distance between these two spacecraft at an altitude of 50 kilometers above the surface. As these two spacecraft orbited the moon once every 2 hours, the moon slowly rotated underneath them. So we had a global mapping of the entire surface. And in principle, the way this works is that whenever there's a mass anomaly, such as a mountain on the surface, it's going to pull on these two spacecraft differently. And because of that, the distance between these two spacecraft will change as the gravity field of the underlying planet changes. And by measuring how the changes in distance vary across the moon's surface, we can put this into a complicated model and make an inversion for the moon's gravity field. Okay, so this here is a map of the moon's gravity field before the GRAIL mission. It's a global image. The near side is on the far left and on the far right, and the far side is in the center. And what you can see is that the far side gravity field is very poorly known. It's very noisy, there's lots of stripes, and it's not clear whether any of the signal is actually real or not. But after only 1 month of mapping from orbit with the GRAIL mission, we were able to fill in this hole of data on the far side and improve the resolution of the gravity field everywhere by orders of magnitude. And just like to emphasize that this map here is only after 1 month of data from the primary mission. We still had 2 more months of the primary mission left, and also an extended mission later in. Okay, so this here is just to emphasize that the spatial resolution of the gravity field is roughly proportional to the distance between the spacecraft and the surface of the moon. So the closer you are to the surface, the higher resolution you're going to get. And here what I'm showing is the minimum altitude of mapping at the end of the mission. And what this shows is that in general, at the end of the mission, we had global mapping from altitudes of about 20 kilometers across the surface, which means that we have a roughly 20-kilometer spatial resolution of the moon's gravity field. However, if you look at this, you'll see that there are several regions where the minimum altitude of the spacecraft is considerably lower. In blue, this is roughly about 10 kilometers above the surface. And in this kind of gray color here, we are only a few kilometers above the surface. So even though the GRAIL gravity map has an average spatial resolution of about 20 kilometers, in some places we can actually go down to kilometer scale resolutions. And just to mention here that if you understand spherical harmonics, the latest model that was developed by NASA and Goddard is a spherical harmonic model degreed in order 1,800. So this is a very high resolution, ultra high resolution spherical harmonic model. Okay, so what I'm going to do now is just go through some of the initial results, and we'll start with the near side of the moon. This is the side that we can see with our naked eyes. And here on the left-hand side, I'm showing the topography, which was obtained by the laser altimeter on the Lunar Reconnaissance Orbiter mission. And on the right-hand side, I'm showing the free air gravity obtained by the GRAIL mission. And the first thing to point out is that in general, these maps are kind of similar. They're highly correlated. So just an example, whenever you have low elevations, such as this kind of crater over here, when you look at the gravity field, you also have a lower than average gravitational acceleration. And this is just because there's less mass at low elevations, and this gives rise to a lower gravity field. Now, on the other hand, if you look at these kind of mountains with high standing topography over here, there's extra mass at the surface. When you look at the gravity field over here, this gives rise to an enhanced gravitational acceleration. Now, there is one major exception to this kind of rule of the two fields being correlated, and that are the so-called mass-con impact basins. So these are the largest impact basins on the near side, such as Serenitatis, Imbrium, and Crisium. These basins have low elevations, but when you look at the gravity field, they have extremely high positive gravitational accelerations. And this was very enigmatic for several years. And as a result of the GRAIL mission, we think we finally understand this. I don't have time to go into the mass-con question, but the answer is it's related to Mare basalts on the surface, thinning of the crust, and uplift of the underlying mantle. Okay, so let's move to the far side. The far side looks much different than the near side of the moon. And just starting with the topography here, the first thing you see on the far side is there's a huge hole on the far side, which is an impact basin called the South Pole Aitken Impact Basin. Even though this is a huge basin, it's about 2,000 kilometers across, and there's roughly 20 kilometers of relief from the center to the surrounding mountains, when you look at the gravity, you really just don't see anything. And the reason for this is that this basin is very old. It formed when the crust of the moon was very hot, and we believe that this basin is isostatically compensated, similar to the continents on the Earth. And because of this, because it's compensated, there is no appreciable gravity signature associated with it. Another thing to point out is that there are mascons on the far side of the moon, but the number of mascons is smaller and the size of the mascons is smaller as well. So just look at here, this is the Moscoviennes impact basin. There is a small mascon in its interior, but the size of this mascon is much smaller than what we see on the near side for these other basins. So this is a big question, is why is the near side of the moon different than the far side? And this is something that I'll come back to later at the end of my talk. Okay, so one of the first quantitative things we can do with the GRAIL data is to make an estimate of the bulk density of the crust. And the reason for this is that the largest signal that we see in the gravity signature is just due to variations in surface topography. And the gravitational acceleration of this topography is just proportional to the density. So it's very easy to invert for crustal density. And this is a map with the near side on the left and the far side on the right. And these white regions, these are just regions where we couldn't perform our analysis because there's Mare basalts there. And the first thing I want to point out is that the average value for the bulk density of the crust is about 2,500 kilograms per cubic meter. Now, this number might not mean much to you, but I just want to point out is that the density, the number that we expected was considerably higher. In particular, just based on the composition of the rocks that we picked up on the surface of the moon, we know that the density of the minerals that make up the crust are roughly 2,800. So why is the bulk density of the crust lower than the density of the minerals that we expect? Well, the most likely explanation is that the moon's crust is highly fractured. There's lots of pore space, and that this porosity, it leads to a reduction in the bulk density of the crust. And based on the estimates of the composition of the surface, we can actually estimate what the porosity is, and that's roughly about 13%. Now, 13%, to me, that seemed like a lot, but it turns out that 13% is actually very comparable to what you would expect when you look at shocked meteorites. And also when you look at the rocks from impact craters on the Earth, such as the Chicxulub impact crater in the Yucatan Peninsula in Mexico. Okay, so here, what I'm showing, this is a map of the porosity of one of the large impact basins on the moon, Hertzsprung, which is a crater that's about 600 kilometers in diameter. So this here is showing a shaded relief map, and this circle is the main rim of the basin. And then here we have the peak ring of the basin. And on the right-hand side, we show the GRAIL estimated porosity of the crustal materials. And what we see is that in the interior of the peak ring, the porosity of the crust is very, very low. And the reason that this is low is that this is exactly where we expect the impact event to melt the crust and form a very thick impact melt sheet. And when this impact melt sheet crystallizes, it forms naturally with zero porosity. So this is why the porosity is very low in the interior of this basin. Now, when you look near the rim of the crater and further out, the porosity is substantially higher than average. And our explanation for this is twofold. First, we think that when you excavate materials from the center of the crater, you deposit them as ejecta on the surface close to the rim. And these materials will be highly fractured and have lots of porosity. And a second thing is that when you form the crater, there's going to be a shock wave that passes through the crust, and this shock wave can fracture the pre-existing crust. So it's a combination of these two factors that give rise to these high porosities that are found close to the crater rim. Okay, so for the moon, we know the gravity field, we know the topography, and as I just showed you, we also know the bulk density of the crust. So with these things, one of the first things we can do is to create what's called the Bouguer gravity anomaly. And if you never heard of the Bouguer gravity, it's very simple. It's in essence just the observed gravity minus the gravity that you would predict from the surface topography. And what's good about the Bouguer gravity is that it pretty much tells you what is going on below the surface, tens of kilometers below the surface. And as you can see here, the Bouguer gravity map is very smooth compared to the free air gravity. And the largest signals that you see are associated with the impact basins. And the first thing that we can do with the Bouguer gravity is to use this to invert for the thickness of the crust. So the GRAIL's interpretation of the origin of these Bouguer gravity anomalies is that the only thing that's happening is that there is relief along the crust mantle interface, and that this gives rise to variations in thickness of the crust, which is the origin of these Bouguer anomalies. So this is one of the crustal thickness inversions that came out of this study. And this map, you've probably seen it before, and shouldn't be too surprising. In general, what we see is that wherever you have an impact basin, the crust of the moon is thin. And this is not surprising because when you form a large impact, it's in essence a big explosion, and you dig up lots of materials from the crust and then throw them out over the surface of the moon. And this thins the crust in the process. Now, what is surprising to me is that there are a few impact basins where the crust is predicted to be, where the thickness of the crust is predicted to be close to zero. And this is in particular for the Chien-Shiung impact basin on the near side and the Moscoviennes impact basin on the far side. And what this suggests to me is that these two basins might have excavated all the way through the crust and into the underlying mantle of the moon. And that maybe the mantle of the moon is going to be exposed on the surface. So I will talk about this later at the end of very end of my talk. Okay, so continuing on with impact basins, one of the things that GRAIL was able to do was able to actually discover new impact basins that were very old or either degraded by younger impact basins. So just to give you an example of this, this is topography on the left and then the Bouguer gravity on the right. And this impact basin called Lorentz, this is a well-known impact basin on the far side of the moon. And when you look at the gravity field, you see there's a very standard high Bouguer gravity anomaly associated with the interior of the peak ring of the basin. Now, what was kind of surprising to us is that if you look just to the southeast, there is another large positive Bouguer gravity anomaly that doesn't appear to be associated with anything. If you look over here in the topography, it's not clear to me by looking at the topography map, but it doesn't look like there's an impact basin here. But when you look at the gravity, it's clear that there's something there. And the GRAIL interpretation is that this is an ancient impact basin that formed before the Lorentz basin. And what happened in essence is that this basin formed first, the Lorentz basin formed later, and because the Lorentz basin is so close, it just degraded the topographic signature of the basin, so we can't see it in the visible imagery. But GRAIL is great because GRAIL can see below the surface, and this is why we can actually still see remnants of this impact basin in the gravity data. And this here is showing another example. There's lots of examples I could show, but this is just one more. Here, if you look in the topography, there's really nothing really very interesting in this left image. But when you look in the gravity map of the same region, you can see that there is a large positive central Bouguer gravity anomaly. And this is most likely due to an ancient impact basin. Again, we can't see this basin in the topography, but it is visible in the gravity because gravity tells us what's going on below the surface. So as a result of this, one of the great things that came out of the GRAIL mission is that I think we have the first complete and unbiased inventory of all lunar impact basins. And this is very important because if you read through the lunar literature, there's a lot of debate as to how many impact basins there are on the moon. And there's also a lot of debate as to what is the size of each of these basins. And the reason for this is that, as you're probably aware, most of the lunar impact basins are classified as so-called multi-ring impact basins. And it's not really clear which of the rings of these basins corresponds to the size of the basin. But because of the GRAIL gravity signature, this provides us an unambiguous metric to determine the size of any impact structure. And this is just showing the cumulative size frequency distribution of all impact basins on the moon mapped by GRAIL. Okay, so this is based on this data set, we found something that I think is very surprising. And just naively looking at this crustal thickness map, it appears as if there are more large impact basins on the near side of the moon than on the far side. So for example, in this crustal thickness map here, there are 8 circled basins here, which have sizes which are greater than about 300 kilometers in diameter. And on the far side, there's only 1 basin with a comparable size. And I would say that this one basin, the South Polacan Basin, is atypical, so you should ignore it. So just based on this map looking here, it looks like there's more large impact basins on the near side than the far side. And the obvious question is, why is this the case? Well, the GRAIL team interpretation of this is that this has to do with the temperature of the moon's crust and mantle. And in particular, we think that the near side of the moon is hotter than the far side of the moon. So why is this? Well, this here is showing a map of the abundance of thorium, which is one of the primary radioactive minerals that keeps planets hot over geologic time. And as is well known, most of the moon's radioactive material is located in a single geologic province on the near side of the moon, in this region here, which is called the Procolarum creep terrain. Now, if you make a thermal evolution model and see what happens, this is what I'm going to show on the right. And this is just a thermal evolution model where we put a bunch of radioactive materials in the crust and we run this forward in time. And what you see is that this region of the moon heats up over time. You melt the underlying mantle, which gives rise to the Mare basalts. And then even today, 4.5 billion years later, after we started this simulation, the near side crust and mantle is hotter than the far side crust and mantle. So the question is, could this difference in temperature affect the basin forming process and make craters on the near side look bigger than they actually are? So to address this, we did some ISAIL hydrocode simulations. These is just simulations of an impact forming process where we ran 2 simulations which are nearly identical. And the only major difference is that one simulation, the crust is hot, and in the other simulation, the crust is cold. So here on the top, we're showing the case of an impact onto a hot crust on the near side of the moon. And on the bottom, we're showing the impact onto a cold crust on the far side of the moon. And in this image, there's a lot going on, but the colors here on the right correspond to composition. So this brown is the mantle and this gray is the crust. And these dashed lines here correspond to where is the final rim, the final size of the crater. So let's run these forward in time. So what these simulations show is that only as a result of the temperature, the basin forming process is different. And in particular, for the case where the crust is hotter, the final size of the impact basin is going to be larger by roughly a factor of 2. So you can see here, the peak ring here is at a radius of roughly 200 kilometers, but in the cold case, it's at roughly a diameter of roughly 100 kilometers. And the reason for this is that in this case here, the crust and mantle have a lower viscosity and it's easier to push the crustal materials out of the way. So just because of this difference in viscosity between these high temperature and low temperature cases, basins form within a larger size in a hot target than they do in a cold target. Okay, so here is just showing the distribution and sizes of large impact basins on the moon. This is what we see on the far left-hand side. And what we did here is we corrected the size of these impact basins for temperature. So if the near side crust of the moon had the same temperature as the far side, this is what we would see in the center. The basins would be smaller by roughly a factor of 2. And when you compare this map here with that on the far right, you can see that the distribution and size of impact basins is statistically more or less the same. So when you correct the size of the basins for temperature, the near and far side of the moon are roughly the same in terms of the number and sizes of impact basins. Okay, so the last thing I'm going to talk about is the mantle of the moon. And this is just a cross-section of the moon showing that the moon has a crust, a mantle, and a core. But what's important is that roughly, in terms of volume, the most important region of the moon is the mantle. Just in terms of volume, roughly 95% of the moon is composed of mantle materials. However, to date, we don't have any samples of the mantle, and no samples of it have been identified in remote sensing or in the sample collection. And the only way to make inferences about the mantle composition is through geophysical data or through looking at the composition of the Mare basalts, which are derived from the mantle. But with GRAIL, it turns out that GRAIL suggests that we may in fact have samples of the mantle on the surface of the moon that we can actually investigate. So I'm showing a crustal thickness map of the moon. And as I previously showed, the thickness of the crust within the Chrysium impact basin and the Moscoviense impact basin is close to 0. And this suggests that perhaps these two basins excavated all the way through the crust and into the underlying mantle. Now, we have another interesting data set, which is from some spectral reflectance data from the Kaguya mission. And this is from a paper of Yamamoto et al. In 2010. And what they're mapping here is each of these stars corresponds to the location where they detected the occurrences of nearly pure olivine on the surface of the moon. So this would be a rock called a dunite. And the most likely origin for pure olivine is from the mantle of the moon. So what we suggest is that these stars here, in particular those around the Chrysium impact basin and around the Moscoviense basin here, these olivine-rich deposits are likely olivine-rich deposits that were derived from the mantle and that are sitting on top of the surface today. Okay, so again, here we did some impact simulations to see whether the distribution of this olivine-rich material is what you would expect from an impact. And here's just showing one of our simulations for the Moscoviense impact on the far side of the moon. It just shows that you dig a big hole, excavate the crust, the mantle rebounds, and the mantle kind of slips off to the side and forms a thin layer on the crust just exterior to the basin. So how does this show this again? So the crust is excavated from the interior of the basin, the mantle is exposed in the inside of the basin, and on top of that, we have a small thin layer of mantle deposits just exterior to the basin in this region here. So how does this compare with observations? This is showing first of all, there's Mare basalts, which cover up the central portion of the basin, which hides most of the mantle materials from view. But these yellow stars here corresponds to where the olivine-rich deposits are located. And it turns out they're exactly where the impact simulations predict. So we have one occurrence that's just exterior to the Mare basalts here within the peak ring of the basin. And then we have another set of deposits out here, which are just exterior to the peak ring. So I would say that this is a very good comparison between observations and geophysical modeling. And this is just showing another example for the Chrysium impact basin on the near side. This basin is a bit different because it formed in a hot target. But again, here the mantle is entirely exposed. You place Mare basalts on the surface, which hides much of these deposits. But then we still expect that there should be mantle deposits exposed just exterior to the Mare in this region. And that, in fact, is exactly what we see. So if you want to go to the moon and sample the mantle, there's two great places to go to. One is the Moscoviennes impact basin on the far side, and the other is the Crisium impact basin on the near side. Okay, so this is my last slide. So the question is, GRAIL was a very great mission for the moon, and it's unlikely that we're ever going to have another gravity mapping mission from orbit to the moon because the GRAIL data are just so great. So where do we go from here? I think there's a couple things you should keep in mind. The first is that the spatial resolution of most planetary gravity fields is very poor, in particular for Venus, Venus and Mars. So what we need to do is send missions like GRACE, GRAIL, or GOCHE to these other planets like Mercury, Venus, and Mars. Another thing is that with some of these planets, there probably are time variable processes that are affecting the gravitational field. So for example, on Mars, there's processes associated with the formation of the polar caps. And on Venus, there probably are processes associated with volcanism, which could give rise to time variable gravity signatures. So I think we need missions to both of these planets to have long-term monitoring of their gravity fields. And then thirdly, and this is related to the moon, I think we need to put in situ gravimeters on the surface of some of these planets. And these gravimeter measurements will help us to quantify tidal deformation of the planet and also the rotational dynamics associated with the cores of these bodies. And that's all I have to say for today.
Actually, I have a couple of questions to you, Mark.
Sure.
One thing is that you talk about the importance of the Pocalanum crypt terrain. So what is the origin of that place?
Yeah, that's unfortunately, that's probably the biggest mystery in lunar science is the origin of the Procalam Creek terrain. And I look at this kind of very simplistically. The way I look at that is that this is what we actually observe. And then on the right-hand side, here is a thermal evolution model, which shows the consequences of this observed distribution of radioactive elements. But I totally agree that the fundamental question is why is most of the moon's radioactive elements located on the near side of the moon? And there really isn't a very good explanation for this. One explanation is that there might have been a giant impact basin here, and that this thinned the crust, and that most of the moon's kind of creep-rich materials from the magma ocean filled in this impact basin. There is another hypothesis that most of the moon's creep-rich materials sank to the interior of the moon, but then there was some kind of convective instability where the creep-rich materials came back up to the surface in a giant plume. So there's a few different ideas that have been put forth, and honestly, I don't think any of them are very good. So to me, this is a fundamental question about lunar science. I think the one thing that no one will debate is the observations, is that creep is concentrated on the near side of the moon. And if you run any type of thermal evolution model, you need to take into account this observation.
Okay, good. The other question I have is that, so with the GRAIL gravity map, you have found several, if not many, hidden impact basins from the old time, right? Is it possible to reconstruct the impact chronology since you have found these big basins?
Yeah. There's a couple things to say about that. So the first thing I would say is, in general, no. What you'd like to do is know the age of each of these basins, and that can help us constrain the impact flux over time. And there is this theory that there was a so-called late heavy bombardment where there was a peak in the impact cratering rate around 4 billion years ago. And this is something that could be tested if we knew the age of each of these basins. But unfortunately, the only way that we can estimate the age, well, there's two ways we can estimate the age of the basin. One is that we can either have samples, such as from the Apollo mission, or we can count the number of craters that are superposed on top of the basin. And for some basins, we can actually do this. But unfortunately, with the basins that are completely been buried and been totally destroyed, and they have no topographic signature whatsoever, and the only thing that we see is their gravitational anomaly, we can't really say anything about their age except that they're very old. And unfortunately, that's not good enough in order to address the question that you're looking at. But another question is that we want to find out what is the actual size of the basin. And this here is just showing that the size of this Bouguer gravity anomaly here corresponds very closely to the size of the peak ring of the basin. And so if we can actually measure the diameter of the Bouguer gravity anomaly, that gives us the size of the peak ring of the basin. And then based on some scaling relationships, we know that the crater size itself is roughly 2 times the size of the peak ring. So we can get very good information about the size of the basin from the gravity, but unfortunately, we can't get much information about the age of the basin.
But do you believe in the late heavy bombardment event theory?
Do I believe in it? So I very close to my office is a researcher called Alessandro Morbidelli, and he is one of the main proponents of this late heavy bombardment theory. And recently we had a paper together about 2 years ago where he kind of revised his thinking about the late heavy bombardment. And I think his view today is that there probably was a very high cratering rate very, very, very early in lunar history. But by early, I mean 4.4 billion years ago. And then after this, the cratering rate just slowly declined with time. So I don't think that he actually believes in this kind of idea of the late heavy bombardment anymore. But it's a question that's very hard to address, because in my opinion, the only way you can do this is by dating the ages of the impact basins. And the only way to do that with fidelity is to actually go there and collect samples so that you actually have an absolute radiometric age of the basin. And I would say that there's only a few basins that have been dated in this manner. We dated the Imbrium impact basin, which is well known at 3.85 billion years old. Some people think we dated the Serenitatis basin from the Apollo 17 mission, but there's a lot of people who aren't certain about that age, who think that we actually just collected materials from the Imbrium basin. And there's also some people who think that we dated the Nectaris basin from samples collected at the Apollo 16 mission. But again, there's lots of people who think that most of the samples collected on the surface are actually derived from the younger Imbrium impact basin. So I think it's a problem that unfortunately is not going to be easy to address without further samples. So I think this is one of the reasons why many space agencies, such as NASA and China and maybe Taiwan as well, want to go to the moon and collect new samples. One of the key places you want to go to is the South Polacan Basin, because the South Polacan Basin is the oldest impact structure on the moon. And if we can date the age of the oldest impact basin, that will give us one constraint on the time frame of the impact bombardment of the moon. And then secondly, the South Polacan Basin hosts a large number of smaller impact structures. So many people think that if we go to the South Polacan Basin and sample a lot of rocks, we will be able to date the South Polacan Basin itself, but also several smaller, younger basins that are superposed on this structure. So I think sample return is very important for resolving the so-called late heavy bombardment idea. And unfortunately, in my opinion, I don't think that we're going to resolve this problem until we have more samples.
Mm-hmm. Okay, one last question. In the last sentence of your slide, you have a very mysterious sentence saying that rotational dynamics of the core. What do you mean?
Yeah, so this concerns mostly the moon. And I would say that this last point here is actually related to one of the science objectives of the GRAIL mission, which in my opinion, we didn't address sufficiently. And one of the science objectives of GRAIL was to actually detect whether the moon has a solid inner core. And the way we were going to do that is that if the moon has a solid inner core, it will be rotating and it will be slightly flattened. And because of the flattening, the core will rotate slightly differently than the rest of the solid portion of the mantle. And this would give rise to a time variable gravity signature that we would see that corresponds to with a period of 1 month. And we were looking for this small time variable gravity signature associated with the inner core of the moon. And unfortunately, we didn't see it. And the question is, does that mean the moon doesn't have a solid inner core, or does that just mean that the GRAIL measurements weren't precise enough to detect the gravity signature coming from the core? And I think one of the ways to address this is actually to put a static gravimeter on the surface and just look at the time variable gravity signatures that we see. And some of these time variable gravity signatures will be just associated with tides, just a tidal deformation of the planet. And there will be another gravitational signature associated with the rotational signature of the solid inner core. So this is kind of what I was aiming for, is that we should put a gravimeter on the surface, and the gravimeter will look at these tidal and core rotational gravitational signatures.
So this gravimeter is different from the seismometer, right?
Yeah, exactly.
It's a different thing.
Yeah, okay. I would say,
go ahead.
In regards to this, I think today there's a general consensus that the moon does have a solid inner core. It's just that there's not much physical evidence for it. For example, if you just do thermal evolution models of the moon and you cool the moon over geologic time, most of these models predict that you will at some point start to crystallize the core of the moon. Also, in terms of looking at the moon's magnetic field, people believe that the moon had a geodynamo in its past. And one of the easy ways to power a geodynamo is by core crystallization, just as you do on the Earth. And then in terms of the measurements to predict whether the moon has a core, one of these is seismology. You can use seismic measurements to detect the core mantle interface and the interface between the liquid and solid core. And there is one study that was published that thought that they did this, but I think most people would agree that the detection of the solid inner core is somewhat ambiguous, and that this paper probably was a bit optimistic in the way that they interpreted their data. So I think really the last way to really address this question is by looking at the gravitational signature of the solid, the gravitational signature associated with the rotation of the solid inner core. And this is something that we should be able to do with a gravimeter on the surface.
Okay, thank you so much, Mark. But you know that I'm going to ask you to give another talk. So please think about what we are going to talk about, right?
I'm happy to give more details about this, and hopefully this will be late next year, because the end of the year.
Yeah, okay.
Wait, can I have a question?
Oh, there's Professor John. He wants to ask a question. Yes.
Yeah. When you talk about the anomaly, the Bouguer anomaly of the gravity field, you mentioned that it's a comparison between the expected field. So in that sense, you actually have to know the elevation or topography of the surface. But how do you know where the surface elevation at the backside of the moon? Right?
Well, we have I kind of showed you one of these, a global topographic map of the moon, and this is the one I showed you is a map of the topography based on laser altimeter measurements from the Lunar Reconnaissance Orbiter mission. And as a result of these missions, we know the shape of the moon everywhere with I would say spatial resolution on the order of hundreds of meters or so. So the shape of the moon is very, very well known. And it's not only the Lunar Reconnaissance Orbiter mission that did this. There was a laser altimeter on the Clementine mission which was one of the early missions in 1994. The Chinese Chang'e 1 mission had a laser altimeter on board as well. And then also with the Kaguya mission, they used a technique of taking stereo imagery of the surface. And from the stereo imagery, you can reconstruct the topography of the surface. So I would say today that the topography of the moon is very, very, very well known. And it's because of this that we can actually calculate the Bouguer gravity.
Yeah, but I mean, I have a little bit difficulty understanding, because if you use the laser altimeter, you have to know the orbit of the satellite. Oh. Yeah. But the orbit of satellite depends on the gravitational field. So yeah. It seems to goes into a loop that you.
Yeah, I would totally agree with you. This is a kind of a process where each time we have a new gravity model, we can reprocess the orbits and then reprocess the old altimetry data. This is not something that I have done myself, so I'm not an expert in this, but I think for the laser altimeter that was on the Lunar Reconnaissance Orbiter, I think the altitude was about 100 kilometers above the surface. And I think when you're at 100-kilometer altitudes, that at that point, variations in the gravity field don't affect the orbit too much. Now, when you get closer to the surface, about 10, 20, 30 kilometers above the surface, then you really need to worry about the perturbations of the underlying gravity field, because that will perturb the orbit of the spacecraft. But I think when you're at 100 kilometers altitudes, these perturbations aren't too important. And as you mentioned, the important thing is that we do have a gravity field now, so that you can reprocess the orbits of all previous spacecraft, and then reprocess all the data that were collected from these spacecraft.
Yeah. Okay. Yeah. Thank you very much.
Okay. Happy. Zhang, are you satisfied?
Yeah. I can understand that for smaller scale this will work, but for larger scale, maybe the orbit of satellite is just not as we expected. Maybe the whole thing is I mean the shape is not as we expected. They could so I'm still a little bit concerned about this.
Well, I think you should be concerned, and I suspect that at this point that, well, just an example for the I know with the data that were collected for Venus during the Magellan mission, they had exactly this problem, where they were using a radar altimeter to make a topographic map of the moon, but the gravity field of the planet wasn't very well known when they were doing that. And as a result of this, there were some systematic biases in the altimeter measurements. And then what happened is at the end of the mission, they had an estimate of the gravitational field, and then they reprocessed all the orbits, and then they reprocessed all of the altimeter measurements. And when they did this, most of the systematic biases that they saw went away. So I think that you should always look at this as a kind of repetitive process where you're continuously improving on the gravity field, you're continuously improving upon the orbits, and then you're continuously improving upon the geolocation of data that were collected from the orbit. So you're never going to have a perfect measurement, but every time there's a new spacecraft mission, you build upon the previous gravity field that was given to you, and you kind of iterate, and things get better over time.
Okay. Very good. Yeah. Maybe we could try sometime. We could try to ask Maria Suber, to talk about this. So, asking her to clarify these.
Very busy, but I'm sure she'd be happy to.
All right. So I would say that Mark suggests that we ask you to talk about it, right? Okay. Thank you, Mark. Thank you so much for taking the time. And then it's a very thorough and very interesting lecture. I mean, people would learn a lot from your talk. And it's now it's 10 o'clock, right? Still in Nice, and have a good day. Thank you so much.
And if any of the students have questions that they'd like to ask me offline,
Right. Yeah.
And I'd be happy to help. And also, the one thing I should have done with this talk is I don't have a list of all the relevant publications that came out of the GRAIL mission. But if you're interested in a specific thing concerning impact basins or concerning even just the mechanisms by how we estimate the gravity field from GRAIL, just let me know and I can send you a list of the relevant papers to help you get started.
Okay, good. Thank you so much for the information. Bye-bye.